This morning we have considered the equations governing small non-radial perturbations around the spherical hydrostatic equilibrium, and we derived by linearization equations for these small perturbations in terms of Eulerian perturbations of velocity, pressure, density, and so on. So the equations we were deriving is first of all here the radial component of the momentum equation. This is the first line, the first equation. Then we have taken the second and third component to eliminate these velocity components or the Eulerian perturbations of these velocity components, and arrived at the version of the mass conservation. This is this equation. So we observe some well-known terms from the radial case, which we studied before, and we observe that the derivatives with respect to the angles theta and phi occur only once we insert it or eliminate we have the second derivative with respect to theta of the pressure perturbation plus 1 over sine squared theta times the second derivative of the pressure perturbation with respect to the angle phi plus cotangent the same combination of the angular derivatives is found for the potential here. So these are the same combinations of the derivatives with respect to the angles theta. Results for the next equation. This is the energy equation and the equation for energy transport. Well, the first part is theta and phi derivatives, and actually it's exactly the same combination of the theta and phi components as before, acting here on the temperature perturbation, which have been acting before on the pressure perturbation. So keep in mind, only these combinations of the angular derivatives appear in the perturbation equations. Finally, the perturbation or the linearized version of the energy transport equation looks very much like its counterpart for the radial perturbations. Well, in addition to momentum, mass conservation, and energy transport, we have to solve the Poisson's equation for the potential, because for the non-radial case we cannot solve this implicitly like in the radial case. Let's have a look whether we have the well, for the Poisson's equation, we also see this. We have the second derivatives with respect to theta, then 1 over sine squared second derivative with respect to the angle phi plus cotangent theta, the first times the first derivative with respect to theta acting on our potential perturbation phi. So always the same combination of angular derivatives appear in this equation. Okay, how can we use or how can we make convenient use of this fact? So we observe finally that all these linearized versions of the equations we consider, they contain differential operators containing the derivatives with respect to theta and phi only in the combination. second derivative with respect to theta, plus 1 over sine squared theta, second derivative with respect to phi, plus cotangent theta times first derivative with respect to theta. Let's call this operator, this is a two-dimensional operator, or an operator which acts on a two-dimensional field. Let's call this minus L squared. And maybe with this notation, you may be already suspecting what this means or what this operator might be interpreted with. Do you know this operator L squared? Remember quantum mechanics? Does anybody? What? Pardon? It's the angular momentum. It's the angular momentum operator which is known from quantum mechanics. Well, quantum mechanics has an extensive literature on all these angular momentum operators, and a representation in space of the angular momentum operator is actually this second order derivative with respect to the angles theta and phi. Okay, how can we make use of our discovery that we have the quantum mechanic angular momentum operator here in our system? Well, we know the properties of the angular momentum operator because we know the eigenfunction of the angular momentum operator. The eigenfunctions of these operators are the spherical harmonics YLM. This is a series, or these are functions, spherical harmonics, which depend on two indices, L and M, and are functions of theta and phi. So these form a complete orthonormal system. You may know what this is from quantum mechanics. A complete orthonormal system, that means we can expand any function of theta and phi in terms of these spherical harmonics, and we can represent completely any function of theta and phi by a sum over, an infinite sum over the spherical harmonics. So we may represent any of our perturbations, Q1 or Q tilde, as a function of r and t and theta and phi as a sum over coefficients Q1 Lm. These now have an index or have a subscript L and M hat, meaning that these only depend on radius and time, times the spherical harmonic YLM only depending on theta and phi. And this is to be taken as an infinite sum over the indices L and M. So what did we achieve by this, by writing it in that way? What did we achieve? Well, we have separated in some sense the RT dependence from the theta and phi dependence. Okay, so we have gained by this trick, we have gained a separation of variables. Okay, now we make use of the fact that the YLMs are the eigenfunctions of the angular momentum operator. That means L squared acting on YLM is simply L times L plus 1, where L is the harmonic degree and is one of these indices of the spherical harmonic YLM. So we can write L squared acting on YLM is L times L plus 1. This is the eigenvalue of the operator L times the times the function Lm. So this operator will not mix different spherical harmonics. Acting on one spherical harmonic, it reproduces the same spherical harmonics with a factor L times L plus 1. It does not mix different spherical harmonics. Okay, so what we have achieved by writing it in this infinite sum, we have achieved a separation of the angular variables, and well, the disadvantage, we have got a an additional parameter in our equations, which is the harmonic degree. Okay, so we have at the cost of an additional harmonic, of an additional parameter, L, which is the harmonic degree, we have separated the angular dependencies, and we have an additional parameter in the remaining partial differential equations, which are partial differential equations in the radial variable and the time variable. Okay, so what we have in principle, because the YLMs form a complete orthonormal system, we have reduced the partial, or we have transformed the partial differential equation in R, T, theta, phi into an infinite set of partial differential equations in R and T with a parameter L. Okay? Well, the fact that we only have L squared as an operator which acts on the angle theta and phi, this means that we don't have a mixture, a confusion or a mixture between the different YLM components. So we have a system of completely independent, by this trick or by this expansion, we have a set of infinitely many partial differential equations containing an index L, but we have lost the angular dependence at the cost of having an infinite set of equations. That okay? So they separate, all these equations are separate and independent because the YLMs are not mixed through the operator L squared, and because they are linearly independent, so we can simply separate each component of YLM and the coefficient of the YLM occurring in the infinite sum over the harmonic, over the spherical harmonics. It may be separated into various equations, one equation per coefficient of an YLM function. Okay, so for simplicity, again, we omit the hat, which we have introduced here, because now we know the function q, which is given in our equation, should in principle have a hat and should in principle have an index or a subscript Lm, but for simplicity we omit this, keeping in mind that of course these quantities will then depend on the harmonic degree L, but no longer on the angle theta and phi. So let's go to the equation and see what happens. Well, the first equation remains essentially unchanged. If we compare it to the original version, we have let's go to the original version. So not much has to be done. So this is the original version. We take each of these quantities, each of the dependent variables, expand them in terms of spherical harmonics. Now, because the spherical harmonics are also orthogonal and linearly independent, so this equation has to be valid for each component, for each coefficient of a spherical harmonic. Nothing happens because there is no derivative with respect to the angles there. What about the next equation, which is the mass conservation? Well, in this case, nothing happens because the YLMs are linearly independent. When here we have the operator L squared acting on the spherical harmonics as well as here, but the operator L squared does not mix the spherical harmonics. So this gives this expression acting on a YLM gives L times L plus 1 times the spherical harmonics. So this and this part, each of them gives L times L plus 1 times the Eulerian pressure perturbation or the Eulerian perturbation of the gravitational potential. So these big expressions reduce to L times L plus 1 times the perturbed pressure and the perturbed gravitational potential. Okay, so the same will happen for the energy equation. Well, here, first of all, we have the potential equation. So this part of the Laplace operator from here to here is nothing but L times L plus 1 over R squared times phi tilde. And then the next one would be here. This is this result here. We have the L squared operator also appearing here in the energy conservation equation. This is L squared acting on T tilde, acting on the spherical harmonics, gives L times L plus 1 times T tilde. And the last one, again, does not contain any derivative with respect to the angle, so this remains unchanged. So we are left with, in the end, with the following system of equations. Well, first of all, the momentum equation, what's remaining from the momentum equation, then the mass conservation equation appear with an L times L plus 1 appearing here, times P tilde plus rho naught times phi tilde. Then we have the Poisson's equation for the potential, and the angular dependencies have disappeared or are condensed in this L times L plus 1 over R squared times phi tilde is equal to 4 pi g rho tilde. Okay, then for the energy conservation equation, we have the first part, which reminds us of the radial problem, plus a term which goes like L times L plus 1 over R squared times the perturbation of the temperature. And finally, the last equation then is the perturbed or the linearized version of the energy transport equation. So it looks very much like the radial problem, but we have an equation for the potential in addition, because the potential cannot be solved implicitly and algebraic in an algebraic form. We have to solve this equation separately or in addition to the other equations. Momentum, mass conservation, energy transport, plus here in this case the equation for the gravitational potential. Well, in addition to these equations, we have, of course, the equations which the stationary or the hydrostatic variables satisfy. This means gravitational hydrostatic equilibrium. It means that for the stationary potential, of course, also Poisson's equation is valid, and that for the stationary configuration, for the hydrostatic configuration, luminosity is given essentially by the diffusion coefficient and the temperature gradient, and also that the run of the luminosity with radius is determined by the nuclear energy generation rate. Keep in mind this. Keep in mind that actually this represents these equations are not really single equations, but they represent an infinite set of equations. For each value of L, we have a single equation, and this is an infinite sequence of equations, or we can consider it as a parameter of the equation and solve the equation for each parameter separately, or taking L, the harmonic degree, as a continuous parameter. So we have a one parametric infinite number of equations, or we have one set, or we may regard it alternatively as an equation with a parameter which has to be solved for any value of the harmonic degree. So this is still a partial differential equation containing the radius and the time as independent variables. Well, all the coefficients of this equation seem to be independent of time. They only depend on the background, on the hydrostatic model, which we have defined before this analysis. So all the coefficients of these equations are time independent. Therefore, we do the same procedure as for the radial case. We also separate not only the angular dependence, but also the time dependence in very much the same way as we did it for the radial perturbations of our hydrostatic star. Well, the question is, why is it possible to gain this separation of the angular dependence from the rest? What is actually necessary to guarantee that we can proceed by a expansion in terms of spherical harmonics and thus somehow remove or separate the angular dependence from the radial and the time dependence? What is actually necessary, or what does guarantee that we can do it in that way? Do you have an idea? Yes, the reason is the coefficients are independent of the angles theta and phi. If they were depending on the angles theta and phi, then our expansion in terms of spherical harmonics would fail, or in other words, then the different components would mix. So then the operator, the angular momentum operator certainly does not mix the different spherical harmonics, but they would be mixed by an angular dependence of the coefficients. So if you take a rotating star which is flat, which has no spherical symmetry, you could not do it by this simple expansion. So in the same way as we can separate the time dependence, because the coefficients are independent of time, we can separate the angular dependence because the coefficients of the differential equation are independent of the angle. So the spherical symmetry of our hydrostatic, spherical symmetry and time independence of our initial model of our hydrostatic model is essential to perform either time separation and the angular separation as it was done here. Okay, so let us perform the time dependence. Well, as for the radial problem, we assume that Q tilde is given by a only radially dependent part of the function Q times the exponential of I omega t, where I omega or omega is again the complex eigenfrequency of our system. By this approach we get a separation of time, and then we end up with a set of ordinary differential equations, because now the only independent variable is the radius or the position r. So we get a system of ordinary differential equations in R. So this is the final result with parameters. Parameters now is the harmonic degree and the eigenfrequency omega, as for the radial problem. And well, there is nothing to be done anymore except for preparing the resulting equations for a numerical treatment. And so as for the radial problem, we will measure the eigenfrequency in units of the dynamical timescale. We will normalize all quantities. We will go from the perturbations to the relative perturbations to get dimensionless quantities. This is one point. we will try to get all the coefficients of our equations dimensionless. And, well, in addition to that, this is a more technical point. Apart from going to the relative quantities, we have to consider what is the dependence of our variables once we go to r equals 0. Once we want to consider, or once we want to calculate a complete stellar model extending to the very center of the star, then it's for numerical reasons, not for analytical reason. For analytical reason, we do not need to do it, but we observe that, for instance, pressure perturbation, temperature perturbation, and the potential perturbation go to 0 with the power r to L. R to power L is the behavior of all these quantities once we go to 0 radius. That means all these quantities become 0 at the same time, and this 0 is a numerically ambiguous quantity. So if you say this both pressure and temperature have to be 0, then this numerically the ratio then of pressure and temperature perturbation is not well defined. You take the 0 of two functions. Numerically, analytically, it's not a problem because the power r to L cancel, and then you have a finite ratio of these two. But numerically, this is pretty bad. We have a ratio of two quantities, which is 0. So the way a solution of the problem is to take out the behavior of the quantities once they approach 0. So to define a quantity p hat, which it does not suffer from this problem. So we take p hat, or we define the p quantity p hat by p tilde is equal to p hat times r to the power L. Then p hat will have a finite value once we approach the center. This is numerically more favorable rather than having quantities which disappear both at the same time, but their ratio is no longer defined. The ratio of p hat to t hat will be well defined even in the center because they are finite. So that's just a remark concerning the numerical treatment and a proper numerical representation, such that also the center of the star or the regions close to the center are numerically well behaved. Not analytically, it just refers to the numerics. Okay. Now, if we do that, and I don't want to go into the details, it's a lot of algebra and lots of transformation which needs to be done, but this does not give too much of physical insight. We have already seen at the example of the radial case how this works and how this is done. Okay, so what we end up with is, well, now I have written here in this case, I have written it in terms of x, which is the relative radius, in terms of x as the independent variable. The equations which we get as the perturbation equation, or the linearized version of the momentum, mass conservation, energy transport plus potential equations. So what we end up with is a system of equation which partially looks quite similar to the radial case. It's not that simple, but there are some terms which we might recover. This is, for instance, alpha times p plus delta times t. This is a term which also appears in the radial case. There is another term which goes, well, no, this is not true. Well, these terms might be recovered. This is the mass conservation equation. Once we go to the next one, this is the momentum equation. You recover the acceleration here. This term is also present in the radial case. Well, the different form also comes from the fact that we have done several transformations and that we are in the Eulerian scheme. So the Eulerian scheme is more convenient in this case, but it also generates many more terms, and it becomes a little bit confusing. I don't want you to look at all these terms. It's just the result, what we get once we apply all these transformations, these normalizations, and taking out the dependence of the variables once we go to r equals 0. It's a rather technical point, and most of these transformations are necessary or are motivated simply by a convenient numerical treatment. But the physics is not much different from that of the radial perturbation equations, apart from the occurrence of the harmonic degree as a new parameter. Okay, so this is mass conservation, the final result. Next one is momentum conservation. Then we have the energy conservation. You recover the I sigma term. This is where the time derivative of the entropy comes in. This is the condition if the bracket is 0. This means that the system behaves adiabatically. Well, there are many other terms. There we have somewhere should be the epsilon terms. Well, you have to search for them. Here it is. Here are the epsilon terms. This is the perturbation of the energy generation rate. So this is the final form of the energy equation. Then, of course, we have the energy transport equation, which is, well, this looks more familiar than the other ones before. It contains the kappa p and kappa t terms, and, well, that's it essentially. So this is less confusing than the other equations. And finally, we have two additional equations, which are due to the potential. So the potential, the Poisson's equation, is a second order equation, and we split it into two first order equations. That means this is now these two equations denote Poisson's equation, and we get in the end we do now have a sixth order ordinary differential system containing as a parameter the eigenfrequency, and in addition to the eigenfrequency, the harmonic degree L. So I don't want you to discuss this in detail. It's just as to give you an impression how the final result looks like. The zeta here is the Lagrangian displacement. P, T, well, I promised you some authors take a mixture of Lagrangian and Eulerian variables. Well, I did it myself. Zeta is the relative Lagrangian displacement, but P, T, and L are the relative Eulerian perturbations that are used here. In this, just to complete the notation here, LPH is the luminosity at the photosphere, and rho c is the central density of the star. Phi and psi are the perturbations of the gravitational potential. Well, and as I said before, these equations include a transformation of the variables according to Q going to Q over R to the power L for the numerical treatment of ambiguities in the center of the star. Okay, mainly motivated, these transformations are mainly motivated by a convenient numerical treatment. Of course, what is left? What do we need to discuss? The boundary conditions. Okay, so we need to care about the boundary conditions, and it's quite similar to the radial case. We have a singular point at the center, so we have regularity conditions at the center of the star, and the boundary conditions at the photosphere, at the surface of the star, are ambiguous because our model is not the physical boundary of our star. Okay, so without deriving them in detail, the boundary conditions may be read off from the equations. You write the equations in a form such that all coefficients are regular, do not diverge. Then you get, of course, some factors which make the highest derivatives vanish, like here. So you see x equal to 0. This is the center, is a singular point. Fortunately, it's a regular singular point. Otherwise, it would be pretty bad. We couldn't interpret the solutions. So this term, all the quantities are required to remain finite. That means the left-hand side vanishes for x equal to 0, and it does so for all of these equations. Then we obtain, well, so we might obtain six regularity conditions, and fortunately it turns out each two of them are identical. So they occur in pairs. For instance, from the first and second equation, we obtain two regularity conditions which turn out to be identical. And from the next two equations, we obtain regularity conditions which fortunately turn out to be identical. The right-hand side, the left-hand side and the right-hand side vanishes, and the two conditions which are obtained from that are identical. And the same is true for the potential equations. So we get, for regularity reasons, we have three regularity conditions at the center. One of them is for the potential, psi equal to phi is one condition. Then we have pressure is given by the Lagrangian displacement, and the luminosity perturbation can be expressed in terms of the temperature perturbations. These are the three regularity conditions which are found directly from the equations, which need to be adopted in order to avoid irregular solutions. Okay, now we turn to the outer boundary, to the surface or to the photosphere. I already mentioned, similar to the radial case, these conditions are ambiguous, and one of them is the same as for the radial perturbations. It consists of Stefan Boltzmann's law. This is the linearized version of the Stefan Boltzmann's law in the variables, in the dependent variables, which we have used in this case. Well, another boundary condition is obtained by the requirement that we want to have a force-free boundary. Previously, in the case of radial perturbation, it was that the Lagrangian pressure perturbation vanishes. In the same condition, Lagrangian, not Eulerian, Lagrangian pressure perturbation to vanish is in the new variables given by pressure is given by a linear combination of the Lagrangian displacement plus the perturbation of the potential. Why should we take Lagrangian pressure perturbation to 0 and not the Eulerian one? I think I commented on that this morning already. Well, you can perturb the surface of the star, and what you want is that at the co-moving surface, so to say, if you have a vacuum outside and your star inside with a finite pressure, then you would want that at the perturbed surface, the pressure perturbation should be 0. And that means that the co-moving pressure perturbation should be taken to be 0 and not the pressure perturbation at one fixed point, because the surface of our star is allowed to move. Okay? So this is the Lagrangian pressure perturbation, which is set to 0. And for the potential, we have an additional condition, a boundary condition. This condition is derived from the assumption or from the requirement that outside our star we have a a vacuum solution for the gravitational potential. Outside our star, we assume there is vacuum. So the solution which you're looking for is Poisson's equation in the form delta Laplace operator acting on potential is 0 there. So we have a solution in the vacuum for the potential, and this solution of the vacuum solution should continuously be connected to the potential inside our star. And this condition of continuous connection of the potential to the vacuum solution gives you that psi is equal to minus 2L times the potential perturbation phi. Okay, that's for the boundary conditions. We do now have a sixth order boundary eigenvalue problem, very much like the one for the radial perturbation, with 3 boundary conditions at the center of the star and 3 boundary conditions at the surface of the star. Okay, what is different once we compare it to the radial problem, which is the case L equals to 0? Well, it is, compared to the radial problem, it's of 6th order rather than of 4th order. Else, there is not a big difference between these two systems, both concerning the physics and both concerning the mathematics. So, radial problem is 4th order, and the non-radial problem is of 6th order. So, we need to solve a higher order problem, which caused in former times a big problem, because the higher the order of the differential system was, the more complicated and the more work had to be done numerically for this in this case. Of course, there is some physics which is entering now once we consider non-radial perturbations, for instance, which effect will be coming in, which is not present once we consider radial perturbations. What will? Okay, I think we are at the end. Okay. What is physically? What is there any new physical effect which we expect once we consider non-radial perturbations rather than radial ones? Can you think of? Yes, buoyancy will certainly now come in, because radial perturbations would prevent or would not allow for buoyancy effects. Now buoyancy effects are expected to play a role, but the input physics is not very much different from that what we did for the radial case. The same physics input was there, but the result of considering a non-radial or a non-spherical perturbation rather than a spherical one will be to allow for some additional physical effects. And we will study them in the following lectures in detail. Okay, now we have either a 4th order or a 6th order problem, boundary eigenvalue problem, and we would like to solve it. Analytical solution is not possible, so we have to resort to a numerical solution. And the question is now how to solve this 4th order or 6th order differential problem, boundary eigenvalue problem. May I now have? Okay, thanks. So, the mathematical structure of the linear perturbation equations and their solution. Okay, we have the mathematical problem consists of solving a system of ordinary differential equations for complex variables of 4th order in the radial case or 6th order in the non-radial case. Well, if we combine all the dependent variables in a vector y and denote the independent variable by x, we may write this equation or this system of equation in the following form. Y dash, this vector, is a big matrix times the vector of the dependent variables. This is a short way to describe or short way to write the differential equation in a matrix vector form. And Z is a 4 by 4 radial or by 6 by 6 non-radial matrix containing all the coefficients of the differential equations. It's a complex matrix because these coefficients are not all real, but there are also complex coefficients available in this matrix. The coefficients depend on the background stellar model. They depend on radius or mass, or on the independent variable x. So they depend on x, on the stellar model, and they depend on the two additional parameters, which is harmonic degree and the eigenfrequency sigma. Okay, now we have boundary conditions for these for this differential system of differential equations, and we would like to know how to solve this equation, this system of equations. That's already said. Z contains eigenfrequency and harmonic degree, and 2 or 3 boundary conditions are prescribed at any of the boundary, 2 for radial, 3 for non-radial. Okay, so what is done usually to solve this, to solve these problems? The first and the oldest methods are matrix methods. Matrix methods are work as follows. We split our integration intervals into n points. Points xi. Here I have taken out 3 points, xi minus 1, xi and xi plus 1, and our dependent variables are defined on these grid points. So we define a numerical grid, and we define the grid points, and we define the values of the quantities ui at these grid points. Ui means u at the grid point xi. Okay, well, the dependent variables are parameterized in this way, and the derivatives in the simplest case may then be given by value of u at point I plus 1 minus u at the point I divided by the difference of the grid points xi plus 1 minus xi. This is the simplest way to represent the derivative which occurs on the left-hand side of our equation, the y dash. That's the y dash here. The y dash contain derivatives, and these derivatives may be represented simply by differences with of the variables, the dependent variables, at two neighboring grid points. What we obtain by separating or by discretizing our system of equations is we get a huge algebraic system. So our matrix Z is now decomposed into even smaller parts. We have that the vector of each dependent variables contains now a vector of n values of the respective variables at the various grid points. So we, instead of the quantity u, which is the dependent variable, we have a vector of the length n, where n is the number of grid points, and u1 means it is the value of u at grid point 1. Un is the value at the grid point n. So all the dependent variables now correspond to vectors whose length is equal to the number of grid points. And these vectors are contained in the vector u here, and u consists of the vector containing the temperature, for instance, containing the vector of pressure and case we have 4 equations. Since it's complex, times 2 times the number of grid points, and 6 times 2 times n in the case of non-radial case. So this matrix A still depends on the eigen. This becomes, if you have many grid points, if you want to have a high resolution, this becomes a very, very big matrix. And the eigenfrequency which we are looking for is determined by the equation that the linear equation that the matrix necessary condition for this linear equation to hold is that the determinant of this matrix as a function of the frequency, eigenfrequency, should be 0. That means the 0 of the determinant of this big matrix to determine the eigenvalues. Well, this method faces some problem because this determinant, the zeros of this determinant need to be determined by iterative process. From some other approximation, and this approximation is not necessarily adapted to the problem. So you don't have, usually you don't have good estimates for the iteration of your eigenvalues. You never know how your perturbations look like as a function of radius. Once you start with, the run or the behavior of your function u is not known a priori. A posteriori, and if you go to higher order modes, which have many nodes, then the resolution you need increases drastically, and this might lead to the result that this determinant A becomes ill-conditioned, and you cannot determine its zeros anymore once the system becomes too big. If this equation becomes too big, too many members, then you face difficulties because the matrix A is ill-conditioned and you cannot solve this equation to sufficient accuracy. The problem that for the iteration we need to know the optimum distribution of grid points. Okay, an alternative to now. What is a shooting method? Okay, we treat the system of equations as from one boundary and try to reach the other boundary and to satisfy the remaining boundary conditions at the second boundary. Well, this has the advantage that we don't need to solution, and you can adjust during integration, you can adjust the time step, the integration step according to the run of your solutions. So locally you can ask how fast do our of the shooting methods. So the resolution problems are gone, and we can start here with the two or three known boundary conditions, and we can try to iterate then our shooting until we match the then we integrate to here and see, well, it's not yet satisfied. We iterate our initial boundary condition, do it once again, and iterate our two unknown initial boundary conditions until we match the boundary conditions here. Conditions, which we do not know a priori, and we have to iterate them, so to say, a two-dimensional or even a three-dimensional parameter space. The advantage here, we do not so this would be an ideal method to solve our linear stability problem. However, unfortunately, it's not that nice, because the iteration of the missing boundary conditions some problems which show how this numerical instability comes about. What is the origin of that numerical instability? And it's usually called the so-called parasitic growth problem. So what happens? Somehow, by the initial value problem, one catches divergent solutions. In the problems, there are in general, for systems of order higher than 2, actually the shooting methods work nicely for systems with order 2 and less. Shooting method works nicely, but for systems higher than second order, we get this numerical problem. And our system are of fourth and sixth order, so we suffer from this problem. So what's going on is there are it in terms of having something like diverging solutions from a regular singular point. In that case, you also have diverging solutions. Here you have diverging solutions for a different reason, but these diverging solutions spoil the entire integration or this solution. So these parasitic growth means the integration catches solutions which you don't want, but which explode exponentially and thus spoil your integration. The advantages of a shooting method: no resolution problem, and otherwise no resolution problem, no problem with determining, no principal problem of determining the eigenfrequency. We don't need any problem. So the aim would be, we would like to have a numerically stable shooting method, And well, to reach a numerically stable method, we should not have an ambiguity in the initial condition, because the ambiguity in the initial condition leads to the capture of this diverging solution. Numerically stable, which might be the fact, because this capture of diverging solution is the reason for the parasitic growth problems. We might be able to use a shooting method to determine the solution. There is, in fact, a method to avoid ambiguous initial condition, which is at the same time numerically stable, which in its nature is a shooting method which does not suffer from resolution. I regret is not very much known among physicists who solve these problems, and also not among mathematicians. So I would like to present you here the use and the results of the so-called Riccati. U and V and 4 matrices A, B, C, and D. So we consider the original system. Y dash is equal to some matrix times Y, and Y contains the dependent variables for the split this matrix Z into 4 matrices. So this is Z, and what we are doing, we split it into 4 parts. This is matrix A, B, C, D, and into 2 parts, U and V. So for the 4x4 system, for the radial case, A, B, C, D is a 2x2 matrices, and these U vectors U and V. Okay. So, and then we rewrite the system is C times U plus D times V, just defining it on the basis of the original problems. Okay? Okay, let's do it for the radial problem. For the radial to convince you, I write down here the first 2 equations of the radial problem. We had zeta dash is C4 times 3 zeta first equation, and the second one for t dash. So this would be the u dash, the derivative of the vector u, which is given by the first 2 components of our original equation. Zeta plus kappa p times p minus 4 minus kappa t times T. Okay, so we can A is the matrix which has to be which has to give the first two components. So U is zeta. So this is 3C4. We just read it off from the equation. So the first component in the A matrix coefficient of delta. This is minus delta times C4. And the second row here is this is minus 4 times nabla 0, and the coefficient, the fourth component, or the fourth 4 minus kappa t times nabla 0. This is very simple to define these matrices. You can simply read nothing behind. Okay, you can do it for the other matrices. You can do it E and D from the original equation, and similarly, of course, for the non-radial system. Now we define a Riccati matrix R, either 2 or 3 by 3 matrix times V. Okay, now let's differentiate this relation and insert from the original equation matrix R. So U dash, of course, U is R times V. U dash is R dash times V plus R times V dash. For U dash, we have the original equation. This is AU. U dash is AU plus BV, and V dash is correspondingly, V dash is given by R times V by definition. This is also here. U is R times V, and we end up with a matrix equation which acts only on the vector V. So collecting all these terms, D minus AR minus B acting on the vector V is 0. Now we haven't specified the vector V. V is arbitrary, so we have that the matrix differential equation has to be the matrix differential equation which does not resort to the vectors u and v anymore. So we express it in the following way. Matrix differential equation means for each matrix element we have a differential equation. That means R differential equation. So what did we achieve? So far, nothing. But, well, let's now have a look for the initial conditions for integration. Well, we can a unique, or we have an unambiguous solution. We have always a solution and a well-defined solution for the matrix R. How do the initial conditions look like? Consider, for instance, the inner boundary, that means the center of the star. we have two regularity conditions there, namely 3 zeta plus alpha p minus delta t is 0, and the second one is that of adiabatic terms, or we can solve it for zeta. So zeta is minus alpha over 3 plus delta over 3 nabla adiabatic. Let's start here. T is P times nabla adiabatic is one case. We can solve also by nabla adiabatic times P. Then we are left with zeta is minus alpha over 3 plus delta over 3 times nabla adiabatic times P. Now go back to our vectors u and v. Okay, we rewrite it in matrix form. This was zeta t was our vector u, and the vector lp was our v vector. And both are connected through the matrix AR. So this would be the matrix if we take u and v at the center, the values at the center, then this would be the value of our R matrix, our Riccati matrix at the center. Now we write these boundary conditions in the matrix form, or we read off from these boundary conditions what the matrix form is. Well, these zeta and t, these are these two variables, depend only on the pressure perturbation. So the coefficient of L will be 0 in any case. The coefficient of P for the first equation is minus alpha over 3 plus delta over 3 nabla adiabatic. And for the second equation, we have a nabla adiabatic here. So what did we receive then? Even if zeta, t, L, and p are not unique, are not unambiguous, there is some degree of freedom in the choice of the boundary conditions in terms of zeta, t, L, and p. Well, what about the Riccati matrix at the inner point, at the bottom point of our integration interval? Is there any degree of freedom in our Riccati matrix? Well, alpha, delta, nabla adiabatic are known from our background model, from the hydrostatic model. So all these coefficients are known, precisely known. There is no degree of freedom, there is no choice how to choose the Riccati matrix at R equal to 0. The same is true for the Riccati matrix at the outer boundary. You can do this procedure for the outer boundary condition and also define a unique, unambiguous Riccati matrix R. Okay? So what does it mean? Now we have achieved what we have wanted, because we wanted to get rid of the ambiguity in the initial conditions for the shooting method. Now we have unique, unambiguous initial condition, and we can start the integration without any ambiguity concerning the initial condition or the boundary conditions. That means we can take this equation and we start an initial value integration with this nonlinear Riccati equation with uniquely or unambiguously defined initial conditions. And this can be done either from the inner boundary or from the outer boundary. It's in any case, both at starting the integration either from the inner or outer boundary condition is equivalent. In any case, we do have unique, unambiguous initial conditions. So we got rid of the ambiguity in the boundary conditions, and I promise you at the same time we have gained numerical stability. So this is a numerically stable way to integrate these equations, and in an unambiguous way to integrate these equations. Well, and it can be done nicely for any size of the system. The size can be, for the Riccati matrix, can be 2 by 2 for the radial case, 3 by 3 for the non-radial case, and even for higher order systems, should they exist, this method can be applied. Okay? So how is the strategy then? If we start here, R is unambiguous. Well, you say, do I have to finish here? Probably. Well, we could have defined our matrix R also in the opposite way. So just saying not U is R times V, but who tells you that you could not just take V is some matrix times U? Well, this would then be, if the inverse of the matrix R would exist, it would be the inverse of the matrix. So you can equivalently define the Riccati equation and also the boundary conditions by assuming the inverse of the Riccati matrix, simply by inverting this relation. This is equivalent to this way to define Riccati matrix, and sometimes it's also needed. For instance, if you the photosphere can only define on the basis of the boundary conditions only the inverse of the matrix. It may happen that it's not possible to define R, but it is possible to define the inverse of this matrix. In that case, either the Riccati matrix or its inverse is provided unambiguously at the boundary. So we have unambiguous initial conditions for R, and A, B, C, D contain the information of the equilibrium stellar model and the parameters L and sigma. So what I said already is, alternatively, we may define V is S times U, with S being the inverse of R, should R2 minus 1 exist. Well, this leads to a Riccati equation which looks very much similar, but where the matrices are simply exchanged. So this leads to a Riccati matrix with S, for S, where simply compared to the Riccati matrix with R, the matrices A have to be exchanged with D, and B has to be exchanged with C. So this is equivalent. Okay, so the last step would then be, how do we determine, we do now know how to integrate it, but how do we determine what is left, namely the determination of the eigenfrequency sigma? Okay, but I think I have to stop here, so I will tell you this next time. Thanks. Yeah, okay.
When we adopted this Riccati method, we
Yes.
went from a linearized system to a non-linear equations.
Yes.
What exactly will happen when we are going from this linearized system? Will you capture some non-linear effects?
Hopefully not. No, we see that the what I try to demonstrate is that the linear system is equivalent to a nonlinear matrix system. This can be explicitly shown. I hope you agree with the derivation. But what do you mean by capturing nonlinear features?
I may be confused by my statement that we are still in a linear system.
Yes,
So,
we're starting from a linear system, and for numerical reasons, we switch to a nonlinear equation. The nonlinear system is numerically more stable than the linear one. The main reason being that we cannot, in the linear system, we cannot formulate the initial conditions for a shooting method in an unambiguous way. We always have to guess the remaining, the conditions which are not known at one boundary. So we only have two boundary conditions, and for an initial value integration we need 4 of them. So we have to guess 2 of them. And this causes the numerical difficulties. Why? Well, I can argue, or I can give some arguments why the linear system is unstable and why it gives, in a shooting method, why it gives problems with parasitic solutions. Unfortunately, I cannot give you a proof why the nonlinear system is stable and does not suffer from the parasitic growth problem. Maybe it has to do with the unique initial conditions, which cannot be formulated in the linear system, but which can be formulated for the nonlinear equation. But I'm not aware of a strict mathematical proof why the Riccati method should be stable. I have not come across. Probably it's pretty difficult to prove that solution of the Riccati method is numerically stable. Does that answer your question? Yes. Well, features of the linear system transferred to the nonlinear system. What I try to show is you can construct from the linear system, you can construct a nonlinear equation. And the nonlinear equation has the advantage that we can formulate the boundary conditions in a unique way for an initial value integration. That's the main point. Whether there is a proof for the stability of the Riccati approach, I'm not aware of. But so far, it always worked. I have never come across a situation when the method has failed. Yeah.
I had a question.
Yes.
Like, when you are going from the shooting method to the Riccati method,
yes.
you are like trying to solve the issue of the divergence problems that arise due to higher order systems, right?
Yes.
So in the shooting method, you had a you still have to define a grid, like.
Yeah, you have a finite grid, of course.
Yes.
Local finite. Locally, it's always a finite grid. You go from integration step to integration step. But in a shooting method, you have the advantage that you can adjust this step locally. If you see if you watch your dependent variables, if they vary a lot, then you take smaller steps. If they vary not as much, then you can take the steps bigger.
Yes. So when you go to the Riccati method, what happens to the grid? Do you still use a similar sort of grid, or do you make any do you change how you define the grids, or?
No, I don't change because it depends on the integrator. What you use, you can use any initial value integrator. It could be a Runge-Kutta or what else. Important is, of course, you adjust your integration step locally to your local needs. So it decides either it's irrelevant whether it's a linear system or non-linear system. The code or the scheme, the numerical scheme, adjusts the time or the integration step simply by looking for the variation of the variables. If the variation of the variables is big, it takes a smaller step. If the variables do not vary much, then the step will become larger. So it's done irrespective of the equation, simply by considering the variation of your dependent variables. Is that sufficient? Okay. For integration, you may take. There are many initial value integrators around, and you can take any of these, which usually they have a variable integration step included. But the integrator is not really important. You can take many of these. The question is which equation you are solving.
So just any adaptive
Yes,
grid
any adaptive
is
method,
fine.
yes, it will be fine.